Okay. So, hello everyone. Welcome to the seventh week of the interaction session or tutorial session on the course on robotics, basics and selected advanced concepts. Just an introduction about me. My name is Soumya and I am a PhD student here at IIT Gandhinagar, and I work in the field of robotics, mainly soft robotics. Okay. So we have been through 6 weeks, and starting right from the TH parameters, kinematics of serial robots, then parallel robots, application of parallel robots. We moved to velocity and static analysis of manipulators, right? Where we saw Jacobians last time. So we had done a couple of questions. I hope all those questions or the tutorial sessions are helpful for you in solving the assignments and understanding the concepts or more practicing the concepts. Okay, so this time we are going to look at redundancy. So I hope you have already gone through the lecture on redundancy and how do we define the resolution of redundancy. A human arm is an example of redundant system because we can move our arms in 6 degrees of freedom, but we do have 7 joints, right? And we'll see what are the advantages of having a redundant system, why this redundancy which is in human arm is helpful. Okay, and then we'll move to flexible robots. So something in the flexible robots are have like many degrees of or many single actuation, and then they can move in all the 6 degrees of freedom. So we'll see at all of these things. Okay, and yeah, one of the things is one of the ways in which we model the flexible robots using Coursera rod or any beam theory actually involves infinite dimensional system. We convert it into finite dimensional system and then we try to solve. Okay, so these are few of the things that we use. Okay, so let's begin with a brief recap of what was covered in the lecture. So, okay, let's see. Okay, so the structure in which we'll be doing this is it was initially fundamental of static force analysis, and then there were some free body diagrams of mechanisms, and then there was force analysis of 4-bar mechanism, then graphical force analysis, and there were some insights, physical meanings and application, and everything was for at last we studied this flexible robots. Right. So, why do we even need force analysis? This is the very first question that we need to answer. Just hold on. Okay. So, this is a very simple question. And why do we even perform force analysis of mechanisms? So, in the mechanism design, we usually start with kinematic analysis. Yeah. Where we determine the position of links, the velocity of links, okay, and acceleration of links. So all of these things are covered in force analysis when we do dynamic, like when we do kinematic analysis, this is covered. Okay, however, these kinematics only tell us how the mechanism moves. This is answered. Okay, how the mechanism move is answered by this. And what is not answered? Not what forces are required to make it move. Okay, this is something that we need answer for. But what happens in real machines? What do we need to know? We need to know what is the input torque required. Hmm? And we need to know what are the forces acting on the joints. And we need to know what are the loads on links. And what are the stresses in the components it should not break. Okay. So without knowing forces, we cannot design the mechanism structurally. So examples can include crankshaft of engines, robotic arms, machine tools, pumps, vehicle suspensions, right? In all these systems, the mechanism must not only move correctly, but must also withstand the forces acting on it. For this reason, we perform the force analysis. Okay. Then there are a couple of types of force analysis. Examples. Types of force analysis. Okay. And the first one we'll start with the static force analysis. What happens here? Static force analysis assumes that the acceleration is zero or inertial forces are negligible. Therefore, sigma F is equal to 0 and sigma M is equal to 0. This means that the mechanism is in static equilibrium. Okay. So the typical cases are slow moving machines or hand operated mechanism. So something in preliminary design stage also can be here. Okay. Where you do not apply force. The inertial forces are negligible. Okay. The second one, so the second force type of force analysis is dynamic force analysis. Okay. So in dynamic force analysis, acceleration exists. Okay. And moment also exists. So dynamic force analysis includes inertial forces, Coriolis forces, and centrifugal forces. Okay. But in this lecture, we'll mostly focus on static force analysis. There are few assumptions in static force analysis, and what are they? Number one, so links are rigid bodies. Okay. So what does that mean? That means that there is no deformation of links. Okay. The second assumption is joints are perfect. What does that mean? There is no friction, no clearance, and no backlash. Okay. The third assumption is weight of links may be neglected until specified. Okay. And the other assumption is that mechanism moves slowly. Therefore, inertial effects are negligible. Okay, then there are types of force in mechanisms. If you have any question, you can ask me. So when analyzing mechanisms, forces appear mainly at joints. So if we classify them, they can be external forces. Okay. So these are the forces applied from outside the mechanism. Yeah. Examples are if there is a load on slider, or if there is a cutting force in machine tools, or let's say there is some load on robotic gripper. So all of them. Okay. The second is input forces or torques. These are the forces supplied to drive the mechanism. The examples are motor torque, hand force, or hydraulic actuator force. So all of these can be your input. Then the other force is joint forces. These are internal forces. Okay. Transmitted through joints. Examples are pin joint reactions or sliding joint reactions. Okay. After this, so these are basically the types of forces and mechanisms. Then there is another concept, two force members. This is one of the most important concepts in force analysis. So what is two force member? It is a body on which only two forces act. Okay. Examples are connecting rods or certain coupler links or tension rods. So for equilibrium, sigma F is equal to 0. If only two forces act, then they must be equal, they must be opposite, they must lie along the same line. That means forces must be collinear. Okay. So for example, if a link AB is a two force member, then the force must act along the line AB. This simplifies analysis significantly. If there are three force members, then if there are three forces acting on it, it is called a three force member. So for equilibrium, sigma F should be equal to 0, sigma of a moment should be equal to 0. So for three non-parallel forces, the line of action must intersect at a single point. Okay. This point is called force concurrency point. Okay. Then we read about free body diagrams. The most important step in force analysis is drawing the free body diagram. A free body diagram means we isolate the body and show all the forces acting on it. So the steps are basically you isolate the link of the robot, remove the surrounding links, replace joints with reaction forces, right? And show all the external forces if acting on it. For example, if a link is connected by a pin joint, then a pin joint can transmit the force in X direction and Y direction. So we represent the reaction as Rx and Ry. Okay. In a pin joint, the joint allows rotation but prevents translation. Okay, translation is not allowed. Therefore, it can transmit two force components, Rx and Ry, but it cannot transmit any moment. Okay. Then in slider joint reaction, the motion is allowed only along the guide direction. Therefore, the reaction is perpendicular to the sliding direction. Example, if the slider moves horizontally, then the reaction is vertical. Okay? Okay. Then uh, there is force analysis of 4-bar mechanism. Okay. This is the most important mechanism. So you already know that the force bar mechanism has a ground link. Yeah, then it has a crank, it has a coupler, and it also has a rocker. Okay, so after this, suppose there are a few forces acting on it. Let's say some input torque T2 and some external load is there on the rocker, which is denoted by F and L for load. So we want to determine the forces at joint, internal link forces or required output torque, all of these. So we need to identify two force members that we discussed. If a link has only two joints and no other loads, it becomes a two force member. Thus the force is acting along the link. So you draw the free body diagram of each of these links, and then you isolate other links, link 2, 3, 4 if you are doing for link 1. For link 3, link 3 usually becomes this two force member. Thus force acts along a coupler. And for link 4, what you can do? Forces can include some reaction from link 3, ground reaction, and some external load. Thus link 4 becomes a 3 force member. So the three forces must be concurrent. Thus their lines of action must intersect at one point. This helps determine the unknown directions. Okay. So this was the major part of force analysis. After this, we have graphical force analysis. Okay. In graphical force analysis, what we did usually space diagrams and force polygons. So space diagram essentially shows the geometry of mechanism and direction of forces. And force polygon shows or basically represents forces as vectors. Yeah. So what are the steps here? You choose some scale, you draw known force and you draw unknown forces in direction, and you close the polygon. If the polygon closes, sigma f is equal to 0. Okay. So suppose we know that if a load is 100 Newton, hold on. Yeah. So suppose we know that load is 100 Newton and the direction is known. We draw a vector of 100 Newton, then construct other forces head to tail and all of that. So the advantages of graphical method that we had was it was good for visual understanding. It was simpler for planar mechanisms, and like it was useful in teaching, but accuracy mainly depends on drawing precisions. Okay. What is analytical force analysis? Modern analysis uses these equations, and we know that sigma fx is equal to 0, sigma fy is equal to 0, and sigma m is equal to 0 for a planar case. So these equations are written for each link. For link I, the combination has to be equal to 0. Okay. So this is what we do in analytical force analysis that we do now. Okay. Now, Mechanical advantage is one important parameter. And what it is? It is output force on input force. It's like T out upon T in. So mechanical advantage varies with mechanism configuration. Near singular configurations, the forces may become extremely large. Okay. Then there is something called transmission angle. Actually, there are many concepts and I won't go into detail for all of them. But if the angle between the coupler and the output link is denoted as mu. So good force transmission occurs when mu is approximately equal to 90 degree. If transmission angle becomes very small, the mechanism becomes insufficient, right? Okay. So there is a practical design inside that engineers try to maintain, that this transmission angle should stay in between 40 degree and 140 degrees, not less than that. Outside this range, the large joint forces appear. Okay. So we have many examples here. For example, there can be a pump mechanism, and the force analysis tells us what is the motor torque required, what is the piston force required, and what are the joint loads, etc. So the motor provides torque, coupler transfers the force, and rocker pushes the piston. Okay. Okay. What would be the problem if we do not do force analysis? What would be the failure if we do not do? So if force analysis is ignored, the pins may shear, the links may bend, and the bearings may fail. Thus, force analysis is essential in mechanical design. Okay. Okay, I hope this is clear. Now, after this, okay, so the main thing is examples that use 4 bars are engine piston mechanism, or if you have seen the robot that was shown in the lecture, they had it was a continuum manipulator and they had multiple discs, and each of the discs was considered. So there was a cable, and then it was considered as a 4 bar mechanism, and it was solved, right, for analytical solution. Other ways are also possible. For example, if you use beam theory, you can assume it to be a rod and work in continuous space. So examples for this 4 bar mechanism are engine piston mechanism, pump linkage, or robotic arms or suspension mechanisms. So force analysis helps us determine the motor torque, joint loads, and it is helpful in structural safety. Okay. Okay. So can a two force member experience bending? Do you think so? No, it does not. Okay. Okay. So I'll explain the things in detail even more, but if we have time, let's move to a few questions. So the questions here are: in a redundant serial robot, by the way, what is a redundant robot? What is this redundancy? It means the degree of,
when lambda greater than degree of freedom.
right, very good. When the degree of freedom of robot is greater than degree of freedom required for task. Okay. So in 3D space, to satisfy an end effector pose, we need, for position we need 3 parameters, and for orientation we also need 3 parameters. Okay. So in total our degrees of freedom are 6. Okay, so the question here is, in a redundant serial robot, the position and orientation of the end effector is not uniquely defined for a given joint variable. The position and orientation of the end effector cannot be determined for given joint variables. There exists no solutions for joint variables for given end effector position and orientation, and there can be infinitely many joint variables for a given end effector position and orientation. Do you guys want to give a try?
I think D.
Yeah, good. That's the correct answer. So, as I said that so 6 DOF is just sufficient for navigation in 3D space. Okay, 7 DOF is redundant. 8 DOF is also redundant. Okay, so human arm has 7 degrees of freedom, and many industrial manipulators are usually 6 degrees of freedom. So what does redundancy means? This means that the robots has more joints than necessary to reach a pose. Okay, for example, if you want to reach here, it can be done using multiple ways. Like there are a couple of joints that would also tweak this and you'll be able to reach this. There is not a unique solution. Okay, so multiple joint configurations can produce the same end effector pose, and for example, a 7 DOF arm reaching the same point can bend its elbow differently. Okay, so if we go for um, let's say mathematical representation, let's say x is equal to fq, where x is our end effector pose and q is the joint variable. So if dimension of q is greater than dimension of x, that means the system is underdetermined and infinite solutions exist. Okay. So there can be infinitely many joint variables for given end effector position and orientation. This is exactly the definition of redundancy. Okay. So as I said, you can rotate the elbow in many ways while the hand remains fixed. Okay. Same pose, but different joint configurations. The first option here was the position and orientation of the end effector is not uniquely defined for given joint variables. This means that same joint variables can lead to multiple poses, but that never happens. Uh, Forward kinematics is deterministic. Okay, for given q, for given q, the pose x is unique, therefore it is not correct. Okay, and the second option is the position and orientation of the end effector cannot be determined for given joint variables. This means forward kinematics cannot be solved, but forward kinematics is always solvable. Given the joint angles, the pose can always be computed, therefore it is incorrect. Okay, and the third option we have, there exists no solution for the joint variables for given end effector position and orientation. So this describes a workspace limitation. Okay, and it is not redundancy. Example, if the target is outside the robot reach, but redundancy actually means more solutions exist, therefore this is also incorrect. Okay, so I think okay, the best example is definitely our human hand. So non-redundant robot has unique joint solution, redundant robot has infinite joint solution. Why do we design redundant robots if 6 DOF is enough? Any answer to this question? Why do we do it? Okay, so I'll tell you. These redundancies are helpful in obstacle avoidance, better manipulability, singularity avoidance, and energy optimization. So if you've gone through the lecture, you might have seen all of these applications coming in, right? So just in one line, I would like to say that redundant robots have more joints than necessary and they have infinite joint configurations for the same end effector pose. Okay. Okay. So the resolution of redundancy in a redundant serial robot deals with obtaining unique inverse kinematics solution, deals with obtaining unique direct kinematic solution, involves imposing additional constraint for obtaining unique direct kinematic solution, is not relevant for the solution of the direct kinematic solution. Okay, so this question is mainly for checking the understanding if people understand the difference between forward kinematics and inverse kinematics of redundant robots. Okay, so uh, okay, anyone wants to take a guess? No? Okay, let's start from very basics. So in forward kinematics, you have the joint variables, right? You have joint variables and then you want to find out end effector pose. In inverse kinematics, you have end effector pose and then you want to find out joint variables. So forward kinematics computes pose from joint angles and inverse kinematics computes joint angles from pose. Okay. So in forward kinematics, given the q, we know that the pose that we are going to obtain would be unique. Mathematically, x is equal to a function of q. There is no ambiguity here, right? And so forward kinematics never has multiple solutions. I'm talking only about serial robots. Okay. What happens in redundant robots? In redundant robots, as we already saw, the degree of freedom of robot is greater than degree of freedom required to do a task. Therefore, for example, we saw a human hand, and then here the inverse kinematics become q is f inverse of x. Because there are no extra joints, we get infinite joint solutions, right? For same pose, we have many joint configurations. What is redundancy resolution then? And redundancy resolution is choosing one joint configuration from infinite inverse kinematic solution. Okay. We impose additional criteria such as minimum joint motion, or we try to avoid the joint limits, or if there is an obstacle, we do obstacle avoidance, we do energy optimization, manipulability maximization. Thus we select only one solution. Okay, so here the first option is it deals with obtaining a unique inverse kinematic solution. This is exactly what redundancy solution does. Since inverse kinematics has infinite solutions, we add criteria to choose one solution. For example, if there is a question to minimize the for example, yeah, so there is we want to minimize the joint variables. If for example, if it is a torque or angle or whatever, if we want to minimize them, okay, or if for example, let's say we want to maximize manipulability, okay, so option A is correct. Okay, now directly let's go to option D, because I want to explain the correct options first. It is not relevant for the solution of the direct kinematics problem. This is also true because direct kinematics does have, if you give the joint variables, then you obtain the force which is unique. So there is no redundancy resolution needed. So this is also correct. Okay. Now let's go to option B. It deals with obtaining unique direct kinematic solution. But direct kinematics already has a unique solution. There is no ambiguity to resolve here, right? So redundancy resolution has nothing to do with forward kinematics. Okay. For option C, it involves imposing additional constraints for obtaining unique direct kinematic solution. So again, forward kinematics is already unique. Additional constraints are only used for inverse kinematics. Therefore, it is incorrect. Okay. So okay, if the hand position, your wrist position is fixed, can the elbow move keeping the wrist position fixed? It can move, right? That means infinite joint solutions exist. So, redundancy resolution means choose one elbow configuration based on some optimization. Okay? So, the main thing is, in forward kinematics, you have unique solution. Redundancy resolution is not needed. In inverse kinematics, you have infinite solution, and then redundancy resolution is required. So, why are redundant robots useful if they complicate inverse kinematics? Obviously, the answers that we had already, that we can have obstacle avoidance, we can have singularity avoidance, we can have joint limit avoidance, and we can have smoother motion. Okay. Okay, let's move to the next question. Redundancy in serial robots can be used. I don't know. I think this is a simple question. Can someone tell me? I am repeating this throughout. Okay, again, this is very simple. It's just that redundancy, I'm repeating the definition so that it sticks in your head. That the number of joint degrees of freedom is greater than degrees of freedom required to do a task. So if task DOF requirement is just 6 degrees of freedom, robot DOF is degrees of freedom is 7. Therefore, infinite solutions exist. This means that robot has extra freedom to optimize the motion. Okay, so redundancy allows optimization. Okay. So, yeah. So, for redundant robots, Q dot is Jacobian pseudo inverse plus I minus, right? The first term here produces required end effector motion, and second term null space motion. Okay, so null space motion does not affect the end effector pose. Okay, so then this null space motion is what allows optimization tasks. Okay, so after this, okay, so if there are two different arm configurations that can reach the same end effector pose, for example, human arm reaching a point while avoiding the wall, because the robot has extra joints, it can bend around the obstacles. Therefore, option A is correct. Then each joint has limits, right? There is some theta min and theta max. So suppose the elbow is close to its limit, redundancy allows another configuration that keeps the elbow away from limits. Okay. So there can be two configurations in which one elbow is fully bent, in the other case elbow is relaxed. So both reach the same point. Therefore, redundancy helps in joint saturation, helps to avoid the joint saturation. Okay. Then the third option is minimize rotation at joints. Sometimes there are many solutions to reach the same pose. So, for example, if there is a joint 1 which uh, rotates 90 degrees, and there is another solution in which joint 1 rotates 20 and joint 2 rotates 15, and you are able to achieve the same position and orientation of the end effector. So, we may choose a solution that minimizes the total joint movement. Okay, so there can be an optimization problem which has minimize Q. Okay, or minimize delta of change in the joint motion, total joint movement. So this reduces the energy consumption, mechanical wear and tear, etc. So C is also correct. For option D, minimizes joint rates during motion. This refers to smooth motion. Sometimes a trajectory may require very high joint speeds. Redundancy allows distributing motion among the joints. So instead of one joint moving very fast at, let's say, 100 degrees per second, okay, we can use combination of joints, 40 degree per second, 30 degree per second, or 30 degree per second, thus minimizing the joint velocities. So our optimization problem in this case can be minimize Q dot. This leads to smoother and safer motion. Hence, option D is also correct. So, these are the advantages of redundancies. I think one of them is not given, which is avoid singularities. Okay. So, redundant robots are widely used in space manipulators, humanoid robots, surgical robots, because flexibility is extremely useful. Okay, so abhi tak whatever we have seen, it appears that redundancy gives us so many advantages. Why don't all robots have very large degrees of freedom? Why do you think so? If redundancy has so much advantage, then all the robots should have very large degrees of freedom. Why don't we go with it? So, even if there are so many advantage, the problems are that the control is complex, the computation may be expensive, would be expensive definitely, and then the inverse kinematics becomes even harder because you increase the number of motors. Okay, and it comes at a higher cost. So redundancy basically allows the optimization of robot motion without changing the end effector pose. Okay. Okay, let's move to the next question. The tractrix based approach, which was presented in the lecture, it minimizes joint velocities of the robot, minimizes Cartesian velocities of the links of the robots, minimizes joint accelerations, or avoids singularities during motion. Okay, let's first understand what does tractrix means. I think you've gone through the lecture and you might already be familiar. So a tractrix is the curve followed by an object that is pulled by a string of constant length. Okay, so as the pulling point moves, the object traces a tractrix curve. One thing is important is the motion of the trailing point is smooth and it minimizes the lateral movement. So you might have seen the robot snake example. This joint moves the least and this moves the most. Okay, so in redundant robots, when the end effector moves, all the intermediate links also move. Okay, but we may want the links to move in a way that produces minimal unnecessary motion, right? ऐसा नहीं है कि if I want to just reach here, this is also moving like this and coming. No, we might not want that. Okay, and then so our goal is, so we want to produce minimal unnecessary motion. What does that mean? That means that we want to reduce the Cartesian velocity of the intermediate links. Okay. The goal is to minimize motion of the robot links in Cartesian space. This leads to a smoother, more efficient motion. What does tractrix method do? So a tractrix based approach, it chooses joint motion so that link motion follows tractrix like paths. That means which results in minimal Cartesian velocities of the links, meaning the links do not swing unnecessarily, motion remains smooth and mechanical stress is also reduced. Okay, the first option that we had here are that minimizes the joint velocities of the robot. This is a different optimization criterion. Common redundancy resolution method is minimum q dot. This minimizes the joint velocities. Okay, but a tractrix approach does not minimize joint velocities directly. It focuses on the Cartesian motion of the links, not joint variables. So option A is incorrect. Let's check option C. It minimizes joint accelerations. So minimizing acceleration corresponds to minimum jerk or smooth trajectory planning. Okay. But the tractrix approach does not target accelerations. It targets the link motion in Cartesian space. So option C is also incorrect. And then the last option is avoid singularities during motion. So singularity avoidance is another redundancy resolution objective. For example, maximize manipulability. That means maximize J transpose. Okay, this keeps the robot away from singularities. However, tractrix based motion does not explicitly handle singularity avoidance. So this is also incorrect. Okay, so what is a bad motion? There is end effector path and all the links are swinging widely. In tractrix motion, end effector path is followed where the links move smoothly and without large lateral motion. So the tractrix method reduces unnecessary link movement. So okay, so that so we saw that it helps in minimizes the Cartesian velocity. Okay, of the robot links. So I think we saw null space motion in redundant robots. Let's move to the next question. The velocity vector of the end of the link in a tractrix based resolution scheme is always pointed towards the goal point. is always perpendicular to the line of the link, along the link, is always along the link and is always 0. Okay. The question is directly about the geometric property of the tractrix motion. The key idea you should understand here is that the trailing point moves along the direction of link. Okay. So let's start with the options. So the question is, the velocity vector of the end of the link in a tractrix-based resolution scheme is always pointed towards this, always perpendicular, always along the link, etc. So, so we saw that tractrix is a curve traced by a point that is pulled by a string of fixed length. So velocity direction of the trailing point is along the string, right? It, it is along the string. So in robotics, string is link and then the trailing point is end of the link. Okay. So velocity of the link end is always along the link direction. This means that the point moves towards the base of the link along the link itself. This avoids unnecessary lateral motion of the links. So the correct option is C. First option, the A option was, it is always pointed towards the goal point. This is not a property of the tractrix curve. The velocity direction is not necessarily pointing towards the final goal. Instead, it depends on the orientation of the link. Okay. So if the link is angled sideways and the velocity is still along the link, so not directly towards the goal, then it is incorrect. Okay. The option B is velocity is perpendicular to the line along the link. Uh, no,
The
this would,
computer screen is not visible.
it's not visible. Just let me check. Uh, Here for me it shows clearly. Should I present again? Uh,
You are audible, but computer screen is not visible.
It's visible, ma'am.
okay, for Shubham it is visible, and from my side also I don't see any hiccup. Can you please rejoin? Because here the motion that I am seeing on my Google Meet screen is perfectly fine. I don't see any lag here. So I think Manas, there is some problem at your end. Please check.
Then there should be network issue.
Yeah, he might be having network issue. Okay, let's move ahead. So yeah, the option that we were checking was, is always perpendicular to the line along the link. So if the velocity would, so the link is like this. If the velocity were perpendicular, it would move in this direction. This would cause sideways motion of the link, which the tractrix method specifically tries to avoid. So the tractrix approach ensures no lateral sliding, hence this is incorrect. Okay. And then option D, it is all velocity is always 0. If velocity were 0, the point would not move at all. But the whole purpose of tractrix scheme is to move smoothly while minimizing unnecessary motion, right? So this is also incorrect. So the correct option is C. Okay. So if you take a dog out for a walk on a leash, you walk forward holding the leash. The dog moves such that its velocity is along the leash. Right? The dog cannot move sideways relative to the leash. It moves along the leash direction. That path is a tractrix curve. Okay, provided the leash is completely taut. Okay. So the tractrix motion property is that velocity of trailing point is always along the link. the link endpoint moves along the link direction, minimizing sideways motion. Okay, let's move to the next question. So in the algorithm for resolution of redundancy of a hyper redundant robot discussed in the lecture, okay, the motion of the head can be in any direction in 3D space. The motion of the head of the second link is the motion of the tail of the first link. The motion of the last link is 0 and the motion of the last link cannot be obtained. Okay, these are the questions. So, in hyper redundant robots, the number of links are very large. Okay, for example, snake robots, tentacle robots, octopus robots, continuum manipulators. So they have a head and then there are a couple of links. Okay, so instead of solving large Jacobian matrices, the algorithm propagates motion link by link. So this algorithm works sequentially along the chain. Motion propagates along the chain. So head motion of the next link is same as the tail motion of the previous link. Okay. So, if I draw it in this way, A, B and C, and A is the head of link 1. Okay, this is L1, this is L2. Link 1, and B is tail of link 1, and it is also head of link 2. Right, and C is tail of link 2. Okay, so velocity of B is shared by both the links. Okay, so the option A is the motion of the head can be in any direction in 3D space. So the head of the robot is the end effector, right? This is the point whose motion is specified by the task. Thus its velocity Vx, Vy and Vz in any direction can be in any direction in 3D space. Therefore, option A is correct. Okay. For option B, the motion of the head of the second link is the motion of the tail of the first link. This is a very basic kinematic continuity condition. Okay. So, velocity of B is same for both the links. So, option B is also correct. In option C, the motion of the last link is 0. This is false. If the head moves, the motion propagates along all the links. Thus, the last link must move to maintain the connectivity. Hence, this is incorrect. And the last option is the motion of the last link cannot be obtained. This is also false. The algorithm actually computes the motion sequentially. Thus, the motion of the last link can be computed. So, it is the best example for all of this is snake robot. Each segment follows the motion of the previous one in snake and the motion propagates like a wave along the body. So hyper redundant motion algorithms do have head motion specified, motion propagates along the links and then shared joints have the same velocity. Okay, so in hyper redundant robots, what happens? The motion propagates link by link. From head to tail. Okay. Let's move to the next question. So in the experiments with the 8-link robot shown in the lecture, the tractrix based approach appears to be the smoothest since the joints near the base moves the least, appear to be more accurate because the chosen motion is slower compared to the others, appear best as it is more simpler and easier to compute, and appears best since the motion of the robot is chosen to show its superiority. Oh, this was a nice option. Okay. So let's recall the tractrix property. Tractrix motion property is velocity of the link is along the link direction. Okay. Sorry, velocity of the link head is along the link direction. So sideways, because of this, sideways motion of the link is minimized. So this makes the motion very smooth. So motion, so if I draw it, let me draw it. If this is head, L1, L2, L3, L4, etc. These are there. So in tractrix motion, link near the end effector move more, right? Link near the base moves very little. So clearly, end links have larger motion and base links have very small motion. This reduces unnecessary movement of the entire body. So when base joints move very little, the robot does not swing widely, the motion becomes stable and the link velocities remain small. Thus the motion looks smooth. Therefore, option A, which said that appear to be smoothest the joints near the base moves the least, is correct. Okay. Option B is appear to be more accurate because the chosen motion is slower compared to the others. Accuracy has nothing to do with tractrix motion. The tractrix method is about minimizing link Cartesian velocities, not about reducing speed for accuracy. So it is also incorrect. Option C is the tractrix so appears best because it is simpler to compute. No, the tractrix approach is not necessarily the simplest algorithm. It involves geometric constraints and the motion propagation is along the links. So the experiment was not demonstrating computational simplicity. Hence it is incorrect. Okay. And the last option is appears best since the motion of the robot is chosen to show its superiority. This statement implies experimental bias, which is not the point in this lecture. Okay. The lecture shows actual motion behavior, not artificially favorable conditions. Hence, it is incorrect. Okay. So, if you imagine a long rope attached to a chain of rods, and if you pull the end smoothly, the rods near the tip move more, and the rods near the handle move less. Thus, a system appears stable and smooth. The Tractrix algorithm produces a similar effect in robot. It minimizes the lateral motion, the base joints move least, and the motions appear smooth. So, in Tractrix motion, most movement happens near the end effector while the base joints move very little, making the motion smooth. Alright, I hope this question is clear. Okay, let's move to the next question. During resolution of redundancy of hyper-redundant robots, as discussed in lecture and shown in experiments, the obstacles are avoided by the use of sensors. Near the obstacle, the velocity of the link is half space away from the obstacle. The velocity of the links are along the tangent to the obstacle. The entire link avoids the obstacle since the size of obstacles are grown to accommodate the collision of the full link. Okay, so the question tests how obstacle avoidance is handled in hyper-redundant robots using the Tractrix based algorithm. So this lecture basically explains this using the geometric constraints on link motion and obstacle enlargement, right? So let's check this. So obstacle avoidance is done using geometric motion constraints and not using sensors, right? Instead, the algorithm controls the velocity direction of the links. Okay. Now, half space concept near obstacles. For example, so basically, one of the things that you might remember that velocity belongs to half space away from obstacle. This means that velocity must not point towards the obstacle. Okay, so if the obstacle is here, the allowed velocities are like this, but not downwards towards the obstacle. Okay, hence the option B, which says that near the velocity, near the obstacle, the velocity of the link is in the half space away from the obstacle, is correct. Okay, so why does half space constraint work? We know that n dot v should be greater than or equal to 0, where n is the outward normal from obstacle and v is velocity of the link. Okay, so if this condition holds, the motion moves away from the obstacle and the collision is avoided. Okay, now regarding obstacle enlargement, if the obstacle is enlarged, if the obstacle is grown by the length of the robot link, that means, so if the link endpoint avoids the enlarged obstacle, the entire link avoids the real obstacle. This is called the configuration space obstacle expansion. Okay, so option D, which said that the entire link avoids the obstacles since the size of the obstacles are grown to accommodate the collision of the full link. Option D is correct. Now, in option A, it was the obstacles are avoided by the use of sensors. Sensors may be used in real robots, but in algorithmic approach, avoidance is done mathematically using velocity constraints. Hence, this is incorrect. And the other option that we have is velocity of the links are along the tangent to the obstacle. So moving along tangent is one possible safe direction, but the algorithm does not require motion strictly tangent. The rule is broader. Velocity must lie in half space away from the obstacle. So many directions satisfy this, hence this is also incorrect. Okay. So if there is a wall and you're moving, you should not move towards the wall. The allowed motion is any side but towards the wall. So this is exactly the half space constraint. So obstacle avoidance in hyper redundant robots, the velocity is constrained to half space away from the obstacles, and the obstacles are enlarged to account for full link lengths. Okay. Okay. Let's move to the next question. So the question here is, snake robots are typically modeled as hyper-redundant robots with many actuated joints, expected to be used in cluttered environments for search and rescue, capable of avoiding obstacles using motion, and designed to carry their own power source, sensors, and computing. This is the most simplest question I saw. Okay. So it's basically testing the concept and application of snake robots, which are a classical example of hyper-redundant robots. So the snake robots are basically discussed in the lecture as systems with many joints that allow flexible motion in complex environments, right? So a snake robot is a robot with many serial links, right? And each joint can rotate. Number of degrees of freedom is very large. The snake robots are hyper-redundant manipulators, okay? Degrees of freedom that it has is more than the degrees of freedom required to do a task. Okay, a snake robot may typically have 20 to 40 joints. This provides extremely flexible motion. So option A is correct. Then snake robots can move through rubble, narrow pipe, collapsed building, or forest debris, right? Because they are slender and flexible, they are ideal for search and rescue operations. So option B is correct. And then for option C, it's about avoiding obstacles. So snake robots can bend around obstacles, change body shape, and exploit redundancy. So the body simply curves around the obstacle. So option C is also correct. And option D is autonomous operation. Basically, in real applications, snake robots are usually self-contained system. They must carry the battery of the power source, sensors, onboard processor, and communication module. For example of the sensors can be camera, IMU, proximity sensors. So this allows them to operate inside collapsed structure where cables are impossible. Thus, option D is also correct. Okay, so yeah, snake robots are hyper redundant mobile manipulators, and they have high flexibility, they have high obstacle navigation, and they can go move to confined space locomotion, and they are adaptable. So NASA snake robot can be used for planetary exploration, and there are many other universities that already have snake robot. Then we can have medical snake robots for endoscopy. You might have already seen in the lecture, right? So the snake robots are hyper redundant robots with many joints designed to navigate cluttered environments autonomously. Okay, now let's move to the next question. So, an endoscope, as discussed in the lecture, is a device to examine the gastrointestinal tract by a medical person. Can be modeled as a hyperredundant robot. Can be modeled as a six-DOF serial robot. Is driven by many actuators. So this question basically connects the medical robotics with the idea of hyper redundancy. It checks whether you guys understand both the real device and its robotic modeling interpretation. Okay, so endoscope is a medical device used to inspect the stomach, examine the intestine, and visualize the internal organs. It is used mainly to examine GI tract. So this is correct. Okay, why it is just not a 6-DOF robot? So option B is it can be modeled as a 6-DOF serial robot. But an endoscope bends continuously, right? It has flexible sections. It behaves like a continuum structure. It is more like a tube of this type. So it does not behave like rigid link 1, rigid link 2, and rigid link 3. This is not limited to 6 degrees of freedom. Okay, so this is not correct. Okay, then the other option is it can be modeled as a hyper redundant robot. Now the robotic viewpoint here is that even though it is flexible, we can model it as many small rigid links. If we approximate the continuum by very small links, which are of very small size, degrees of freedom become very large. Structure becomes hyper redundant. This is exactly how continuum robots are modeled in robotics. Okay, and option D is it's driven by many actuators. Traditional endoscopes were manually manipulated, use cable driven bending mechanisms. They do not have many independent actuators at each small segment. So every robotic endoscope typically uses a few tendons and not one actuator per segment. They are hyper redundant structurally but not actuated at each joint independently. Okay, so for example, if there is a robot and it has one actuator here, and then it has a cable running over here which is wounded into the onto the shaft of the motor, and it is pulling. So this is an example of hyper redundant actuator, but hyper redundant robot, but the actuator is only here, and this cable is being used to bend the robot. So endoscope is a continuum robot. It can be approximated as a hyper redundant serial chain. So this modeling allows us to apply tractrix based control, hyper redundant algorithms, and obstacle avoidance schemes. Okay, so if you can imagine a thin flexible tube inserted inside the body, it moves smoothly around the internal curves. To model mathematically, we discretize it into many small links. This gives continuum to discrete to hyper redundant robot. Okay, so basically an endoscope is a medical inspection device that can be modeled as a hyper redundant serial robot due to its flexible structure. All right, okay, let's move to the next question. The typical model of a human arm up to the wrist has 3 degrees of freedom, 5, 7, or 8. Okay, so this I think I explained several times, but just right, it has a shoulder joint, an elbow joint, and a wrist joint. Okay, we don't count the finger joints here. The shoulder is a ball and socket joint. It independently has three directions. Okay, so it is 3 degrees of freedom. These are flexion, extension, abduction, adduction, and internal external rotation. Okay. For elbow joint, elbow flexion or extension is 1 degree of freedom. But the forearm also has rotation, also allows rotation, which is pronation or supination. So these motion occurs through radius ulna mechanism. Thus, a forearm rotation is also 1 degree of freedom. So the forearm contributes 2 degrees of freedom. Okay. In the wrist joint, it allows two independent motions, flexion extension and radial ulnar deviation. So it also has 2 degrees of freedom. Okay. So the total degrees of freedom that we have are 7. So yeah, this is important in this is the reason many robotic manipulators mimic the human arm. Industrial robots usually have 6, but human arm has 7. Thus, the human arm is redundant for positioning tasks. To specify pose in space, we need 6 degrees of freedom, but we have 7 degrees of freedom. So, we have one redundant degree of freedom. So, if you place your hand on the table, can your elbow move without moving the hand? Yes, the students who are here should try that. I think you'll be able to do. So yes, and the that extra freedom is 7th degree of freedom. All right. So 3 degree of freedom is just shoulder joint. That is why it is incorrect. 5 degrees of freedom is again wrong. 8 degree of freedom is also wrong. We do not have any degree of freedom more than 7. It is 7. All right. So the human arm up to the wrist has 7 degrees of freedom, making it a redundant manipulator for positioning tasks. Okay. Let's move to the next question. As discussed in the lecture, a planar 3R serial manipulator is redundant if only the XY position of the end effector is considered, is redundant if the position and orientation of the end effector is considered, is redundant since the Jacobian matrix is not square, is never redundant. Okay, so let's check. So let's say this is the manipulator and it has 3 angles, theta 1, this is theta 2, and this is theta 3, sorry, theta 2 and theta 3. Okay, so the number of joints is 3, so degrees of freedom are 3. What task we are solving? Redundancy depends on the task. Okay, if the task requires only end effector position, which is x comma y, and as in the first option, then our task dimension is 2, but the robot has 3 joints. So joint DOF is greater than task degrees of freedom. Okay, so 3 is greater than 2, hence this means that infinite joint solutions exist and the robot is redundant. Okay, just hold on. Okay, now consider the full pose x, y and theta. Okay, so task degree of freedom is 3 and robot degree of freedom is also 3. If both of them are equal, there is no redundancy. Okay, so this is wrong because there is no redundancy in this case. It's redundant since the Jacobian matrix is not square. If you write the Jacobian for position, it would be so okay. So if your Jacobian would be del x upon del theta 1, del x up del x upon del theta 2 and del x upon del theta 3. Del y upon del theta 1, del y upon del theta 2 and del y upon del theta 3. So the dimension here is 2 cross 3. But the reason for redundancy is not simply because the Jacobian is non-square, it is because the robot degrees of freedom is greater than the task degrees of freedom. So the statement is not conceptually correct here. Okay. The fourth option is never redundant. This is clearly false. We just saw that if the only position is considered, 3 would be greater than 2 because the joint degrees of freedom would be greater than task degrees of freedom, so redundancy exists. Okay, so infinite joint solutions would be possible, which is exactly redundancy. Okay, let's move to the next question. In the kinematic model of the human arm discussed in the lecture, only 4 joint rotations are considered, as considering all the joints will make the model too complicated. Only 4 joints are considered, as the motion of the hand is constrained to be in a plane. As the motion of the hand is in 3D space, as okay, since 4 joints are enough to make the system redundant. Okay, so from the previous question, we know that human arm has 7 degrees of freedom. For shoulder it is 3, for elbow and forearm it is 2, and for wrist it is 2. So hand motion, in the lecture, hand motion is constrained to a plane. It is directly from the lecture. Okay, so the motion is only in 2D. Okay, thus the model becomes planar. Each joint contributes 1 rotational degree of freedom. Thus, the simplified human arm model becomes 4R manipulator. 4R planar manipulator, not only manipulator. Okay, so the number of joints 4. Why this model was used? The purpose was to demonstrate redundancy. For planar motion, task space is just x and y. Okay, so task degrees of freedom is 2, robot degrees of freedom is 4. Thus, the robot is redundant because 4 is greater than 2. The arm becomes redundant, and this makes easier to demonstrate the tractrix motion, redundancy solution, and smooth arm motion. So the option A that we have is only 4 joint rotations are considered, as considering all the joints will make the model too complicated. This may be practically true, but it is not the actual reason used in the lecture. The lecture explicitly states planar motion constraint. Then the option C is only 4 joints are considered, as the motion of the hand is in 3D space. If the motion were in 3D, we would need more degrees of freedom, not fewer. This is also wrong. The last option is redundancy depends on task dimension, not a fixed number of joints. 4 joints in 3D space is not redundant. Thus, the reasoning is wrong here. Okay. So, planar motion assumption is forearm planar arm, and it is used to demonstrate the redundancy here. Okay, the third hand motion was constrained to a plane. Okay, let's move to the next question. The null space of the Jacobian matrix of the human arm model up to the wrist discussed in the lecture is 1-dimensional, 2-dimensional, 3-dimensional, and does not exist. Okay, so if you recall, the human arm, which was modeled as a planar 4R manipulator that we talked about in the last question, the number of joints are 4, so n is equal to 4. For task space dimension, we have 2 degrees of freedom. So the Jacobian relates joint velocity to the end effector velocity, right? So here x dot is equal to x dot and y dot, and q dot is equal to theta 1 dot, theta 2 dot, theta 3 dot, and theta 4 dot. Okay, so Jacobian size is basically 2 cross 4. So null space dimension is n minus rank of Jacobian. For a typical configuration, rank of Jacobian is equal to 2. Thus 4 minus 2 is equal to 2. So the null space is 2-dimensional. Okay, the physical meaning of null spaces: the arm can move internally while the hand stays fixed. If you place your hand on a table, your elbow can still move, as we saw before. So this internal motion is the null space motion. Okay, the other options are 1-dimensional, No, we get the wrong Jacobian rank. Three-dimensional, which would mean the Jacobian rank has to be 1, which is not the case, and does not exist. Null space exists wherever the degree of freedom of robot is greater than a degree of freedom required to do a task. So 4 is greater than 2 here. So null space definitely exists. So it is also incorrect. Okay. So yeah, the planar 4R human arm model has two-dimensional Jacobian null space because 4 joints control two-dimensional task. Okay. Let's move to the next question. As presented in the lecture, the joint redundancy in the human arm does not make any difference in the motion of the arm, helps in reducing task space errors in reaching task, helps in reducing joint space error in reaching task, helps in learning to adapt to external disturbances. What happened in the lecture? So the human arm has 7 degrees of freedom, but to place the hand in space, we need just 6 degrees of freedom, which is 3 position and 3 orientation. So the arm has one redundant degree of freedom. So that gives us extra flexibility. Okay. So what does this redundancy allow? Redundancy allows the arm to change elbow configuration, redistribute motion among the joints and react to disturbances. So if someone pushes your arm while reaching, you can still reach the target by adjusting the other joints. That's a key idea. Okay. So option D is it helps in learning to adapt to external disturbances because the arm has multiple joint configurations. The brain can learn to adjust the motion strategy. So example disturbances here could be someone pushes the arm, object weight changes or unexpected obstacles are there. So the nervous system can modify joint motions while keeping the hand trajectory correct. Thus redundancy improves motor learning and adaptability. Okay. Option A, it is does not make any difference in the motion of the arm. This is clearly false, right? Because redundancy provides flexibility, adaptability and obstacle avoidance. So it definitely affects arm motion capability. Okay. In option B, it helps in reducing task space errors in the reaching task. So task space error means hand position error. Redundancy does not directly reduce this error. The brain's control system does. Redundancy simply provides extra joint freedom. So it is incorrect. Okay. And option C is it reduces joint space errors. Joint space error refers to errors in joint angles. So, but redundancy actually means many joint configurations are possible. So joint angles are not uniquely defined. Thus this statement is conceptually incorrect again. Okay. So if you are reaching for a cup, let's say, and someone pushes your arm or elbow slightly, even after the disturbance your hand still reaches the cup. Why? Because your arm can configure itself using redundant joints. So it helps in flexibility, adaptability and disturbance rejection. All right. Let's move to the next question. So, as presented in the lecture, when the human arm is subjected to an external force with increasing trials, the error in the reaching task appeared to reduce exponentially. The error distribution appears to become less eccentric with increasing trials. The error in reaching task appeared to be same in all the directions and the error does not depend on the application of the external force. Okay. So if a subject tries to reach a target point with the hand, is basically the experiment. But an external force is applied to the arm. Okay. Due to the external force, the trajectory becomes distorted, right? At the beginning, the brain does not know the disturbance. The hand trajectory deviates from the target. Error is large, definitely. But as the person repeats the task, the brain learns the force field, the nervous system compensates, and the trajectory gradually improves. So, the option A is the errors in reaching task appear to reduce exponentially. Experimental results show that the reaching error follows a curve like ET is e to the power minus kt. Error decreases rapidly at first, then slowly approaches 0. Okay, kind of like this. So option A is correct. Error distribution becomes less eccentric. So at first the error distribution looks elongated at certain directions. Okay. This happens because the disturbance biases the motion in one direction. After learning, the distribution becomes more circular, less eccentric. That means the subject learns to compensate in all the directions. Hence, option B is also correct. For option C, the errors appear to be same in all the directions. At the beginning, this is not true. The disturbance produces directional errors. Thus, errors are anisotropic. So, this is incorrect. And the last option is error does not depend on external force. This is clearly false. Without the external force, the reaching trajectory would be correct. Okay. So, the error occur because of this force field only. So, this is also incorrect. So, the experiment was external disturbance is provided, repeated trials are taken, and the brain adapts and the error decreases. So, when exposed to external disturbances, human reaching errors decrease exponentially and the error distribution becomes more symmetric as the learning occurs. Okay. Let's move to the next question. The miniaturized pneumatic artificial muscles is preferable for actuated endoscope since it can be easily actuated using electrical heating. It can respond more quickly than the competing shape memory alloy actuator. Other actuators such as small electric motor is very expensive or more bulkier, and it is a linear device and it can be controlled easily. So, this MPAM is an actuator that works using compressed air, right? When pressure increases, the muscle contracts. When pressure increases, the muscle contracts. And when the pressure decreases, the muscle expands or relaxes. Okay, these are similar to biological muscles. This MPAM is good for endoscopes because endoscopes require actuators that are very small, lightweight, fast response, and safe for medical environments, right? So MPAM satisfies many of these conditions. And okay, so one of the options is it is faster than shape memory alloy. Shape memory alloy actuators work by heating and cooling metal. Okay, heating leads to contraction, cooling leads to extension. The problem is cooling is slow. Thus, SMA actuators have slow response times. MPAM works using air pressure which changes very quickly. Okay, so MPAM का response speed is much greater than SMA का response speed. So option B is correct. Okay. Let's talk about option C. Electric motors, other actuators such as small electric motors are very expensive and more bulkier. Electric motors require gears, shafts, bearings, rigid transmission, right? In a tiny device like endoscope, these components become heavy, bulky, and expensive. MPM is simply a soft pneumatic tube which is lightweight, compact, and cheap. So option C is correct. Let's go to option A. It can be easily actuated using electrical heating. This describes shape memory alloy, right? And not pneumatic muscles. So MPAM uses compressed air pressure, so it is incorrect. And then in option D, we have it is a linear device and easy to control. Pneumatic artificial muscles are non-linear devices. Their behavior involves non-linear pressure force relationship, hysteresis, compliance. They are not easily controlled linearly. Okay, so MPAM advantages are that it has fast response, it is compact, lightweight, and suitable for medical robots. So MPAM is preferred in actual endoscopes and not SMAs. All right. Okay, let's move to the next question. The model of the braided miniaturized pneumatic artificial muscle, which is MPM, assumes the tube to be a thin cylinder, the tube to be a thin cylinder with internal pressure, the tube to be a thick cylinder with internal pressure, the tube to be a thick cylinder with internal pressure and boundary conditions on the outer surface to represent the braid. So, uh, so if this is a tube, these are the braided fibers. Components are inner elastic tube, braided mesh around the tube and compressed air inside. Okay. So if internal pressure is there, it expands the tube. Braid constraint converts expansion to contraction. All right. So MPAM operates using compressed air. When the pressure increases, the tube expands radially, but the braid restricts the radial expansion and it produces a axial contraction. Okay, similar to a muscle. So why the tube is modeled as a thick cylinder? The tube wall has finite thickness. Thus the stress distribution is analyzed using thick walled cylinder theory. When the class we know that, so if you remember or know sigma r and sigma theta, where this is the radial stress and this is the stress, the tube behaves like a pressurized thick cylinder. The boundary conditions are added because the braid surrounding the tube applies the constraints. So the fibers limit radial expansion, generate axial contraction forces, thus we impose the boundary conditions on outer surface to represent basically the effect of this braid. So outer surface constraint is the braid effect. Okay. Now let's check for the option. So let's go to option D first because it is the correct option. The tube is a thick cylinder with internal pressure and boundary conditions on the outer surface to represent the braid, right? Because it has thick cylinder model, it has internal pressure, it has the boundary conditions representing braid as we discussed. In option A, the tube is a thin cylinder. This ignores the internal pressure effects, braid constraints, okay? In option B, the tube is to be a thin cylinder with internal pressure. This still ignores wall thickness, braid constraints, okay? The tube to be a thick cylinder with internal pressure. This includes pressure but ignores the braid constraint, which is essential. So yeah, it is a thick pressure cylinder with pressure loading and boundary constraints. Okay, the MPM is modeled as a thick walled cylinder subjected to internal pressure with outer boundary constraints representing the braid, right? Okay, I hope this is clear. So the other options are not correct. Let's move to the next question. In the actuated endoscope shown in the lecture, 3 braided miniaturized pneumatic artificial muscles are used for desired redundancy in actuation. Since there is no space for more than 3 MPMs, since with 3 one can get all the required motions, since only 3 can be controlled at the same time. So, the endoscope tip needs to bend in 2 directions, right? Bending in X direction and bending in Y direction. Okay. Now the tip must move, or I should not draw it like this, I should draw it like this. X and Y. Thus a tip must move in any direction in the plane. Now, each MPM can only pull along its axis. So one actuator alone cannot generate arbitrary bending. If 2 actuators are used, motion becomes restricted. Control becomes limited. Thus, we arrange 3 actuators around the tube. Okay. So, these actuators are placed 120 degrees apart. So, the thing is the 3 actuators are used and we can get all required motions with them. Okay. One is the first option is it is used for redundancy. If redundancy were desired, we would use more than 3 actuators, but the design uses exactly the minimum required number. Okay. Then the other option is there is no space. Space limitation is not the main design reason. The reason is kinematic sufficiency and not packaging. So this is also incorrect. Since only three can be controlled at the same time is the last question. Modern control systems can control many actuators. This statement is also incorrect. Okay. So the thing is, actuated endoscope 3 mpm are arranged at 120 degrees, sufficient to produce bending in any direction. Okay, thus 3 mpm actuators are used because they are sufficient to generate all required bending motions of the endoscope tip. Okay, let's move to the last question. So as shown in the lecture, a cable driven robot can be 3D printed and easily made. It is a lightweight, flexible robot actuated with one or more cables. It can be easily modeled and analyzed. It can achieve a desired position or orientation of the free end by use of only one cable. Okay, so what is a cable driven robot? These robots use tensioned cables to produce motion. Okay, for example, if this is a robot, there is a cable running through it. Okay, and it may deform the robot. So the cable pulls the structure, causing the bending or movement. Okay, the first option is it can be 3D printed and easily made. Yes, cable driven robots often have simple mechanical structure, plastic or flexible links, and embedded cable routing channels. So they can be fabricated using 3D printing. The geometry is simple, the low cost fabrication is there, and rapid prototyping is possible. Okay. The second option is it is a lightweight flexible robot actuated with one or more cables. So cable driven robots are commonly used in continuum robots, surgical manipulators, and snake robots. Okay, so they are lightweight, flexible, and compliant. Motion is generated by one or more cables pulling through the structure. So this is also correct. Option C is it can be easily modeled and analyzed. No, they are harder to model. The reason is cable tension constraint is there, non-linear elasticity is there, friction in cable routing is there, slack conditions are there. Thus the model is complex. Okay, and an option D, it can achieve a desired position and orientation of the free end by use of only one cable. A single cable can only pull in one direction. It cannot fully control position and orientation. Multiple cables are required to control the full motion. So this is also incorrect. Okay. So by pulling different cables, the object bends in different directions, and by that we can like have motion in all the 6 degrees of freedom, all the directions. Okay. So the cable-driven robots are lightweight, flexible, low cost, and easy to manufacture. Okay, and they can be easily fabricated, often using 3D printing. All right. I think we are done with today's class. Okay, so in the next class I request you to kindly look at the lecture before coming, because it is sort of more into Lagrangian formulation, and then we have equations of motion, inverse dynamics, and simulation of equations of motion. So, and recursive formulation of dynamics of manipulators. So I think that would be something from where you'll be able to grasp a lot. So I request you to kindly go through this lecture, and if anyone has any question, then we can carry on, else we are done. No questions? Anything that you want to discuss? Okay, so I think there are no more questions. So we'll meet on Monday, next Monday at the same time, 6 to 8 p.m. Okay, thank you for joining the lecture. Bye.